Okay, so this is a very important lecture, and I'm glad that you could make it, because we're going to talk about wellbore stability and how we use the Shear's equations in order to explain tensile fractures and shear fractures in wellbores. So if you remember what we did last time, is that we wrote these equations, which are called the Shear's equations, that they allow us to calculate stresses around the wellbore. And those stresses, that remember that sigma RR is a radial stress, and it goes into this direction. Sigma theta theta is a hoop stress, and also we're going to have a shear stress in this case, which is going to be sigma theta R, which is that one. So this Shear's equation allows us to calculate all those stresses either at the wall of the wellbore or further away. Problem number one of the homework consists on calculating the stresses around the wellbore and plotting those stresses as a surface map or a contour map. As I don't remember if I asked for the surface plot or a contour plot, but it's basically the same. So with these equations now, we can calculate stresses near the wellbore, as I say, or further away. And our objective now is to check if some of those stresses are getting to limits where we get either to tensile failure or to shear failure. So that's where we are going right now. I can take these Shear's equations, and if I were to say I'm just going to calculate stresses right next to the wellbore wall, then R is going to be equal to A. And as soon as I do that, these equations are going to simplify a lot. And what I'm going to get for the case of a vertical wellbore are just these equations. So,
I have a question.
yes.
Are those equations for a vertical wellbore at the wellbore wall?
Yes. Yes.
Do they apply for like further than?
No.
Oh, okay.
No. These are just stresses at the wellbore wall. So if, let's say, if we're making a schematic similar to the one we were doing before, and this is a wellbore, those stresses are just stresses for a thin layer around it. It will be just valid at a position somewhere over here, or somewhere over there, or somewhere around the wellbore. But it's very close to the wellbore. It's at the wellbore wall. So the first thing that we're going to do here is to use this equation in order to compute what are called tensile or drilling-induced tensile fractures. And the result of that is going to give us something which is called a breakdown pressure. I'm going to explain why this is called breakdown a little bit later on. Basically, what we want to do here is to calculate the minimum hoop stress around the wellbore so that I compare that to the tensile strength of the rock, and I check whether the rock is at failure or not. So if I had, say, for example, the maximum principal stress coming in this direction and the minimum in that direction, the angle theta, remember, is going to be always the angle between this stress and a particular element that I'm considering. Where do you expect to have tensile fractures? What is going to be the angle theta?
0, or 90, or 180.
Okay, so then let me write what you said, 0 degrees or
Oh, well, actually, if you're measuring it from like horizontal, then maybe
y90. So you measure it from here. So you say 0 before?
Yeah.
And then the other location with the lowest minimum hoop stress is going to be here. So it's going to be either 180 positive or if you will measure from here, 180 negative. But let's always measure it in this direction. So it's going to be either this or that, right? And you will see that if we replace now in this equation theta equal to 0, what is the cosine of theta equal to 0? Is equal to 1, right? And sigma theta theta, now I'm going to say that the value of the hoop stress is going to get to the value of the tensile strength. So this equation over here, look how I'm going to write it. I'm going to write that the hoop stress is going to reach the tensile strength, and everything over there is the same. Here, this is the same. And now, since this is equal to 1, this is just going to be minus 2 sigma h max minus sigma h min. And our objective is going to be to calculate that pressure of the wellbore that causes the rock to get to tensile failure. And we're going to call that PW. We're going to call it PV. And this one is usually called a breakdown pressure. And I'm going to explain a little bit why breakdown. But if we were to move this PV to the left, then this is going to be negative and negative. This is going to be positive. And then I have 1 sigma h max and negative 2 sigma h max. So it's going to be 1 negative sigma h max. I have 1 positive sigma h min and 2 positive sigma h min. So it's going to be 3 positive sigma h min. And this tensile strength that was negative over here is just going to go over there. And basically, it's as simple as that. The pressure needed in the wellbore in order to cause a tensile fracture, or to be just at the limit in which you will cause a tensile fracture, is this breakdown pressure called PV. And notice that that breakdown pressure has to be higher than the pore pressure according to this number, if all of this will be equal to 0. It depends on the stress anisotropy. So the more stress anisotropy you have, so this is pore pressure, the more stress anisotropy you have, the smaller this value is going to be. And last, and it makes a lot of sense, it depends on tensile strength of the rock. So the stronger the rock, the higher you can go in pressure in the wellbore without causing a tensile fracture. So this one makes lots of sense. It's very intuitive, and this one it's very intuitive too. What about stress anisotropy? Say, for example, that if we have an example of a strike slip regime, and also you were to assume that the faults are at the limit of equilibrium, and we assume a friction angle equal to 30 degrees. What is going to be that summation of those two stresses? So if remember that if this is at the limit of stress equilibrium, and we have, for example, Q equal to 3, then how many times bigger sigma h max is going to be bigger than sigma h min? You remember that what we did, for example, with normal faulting, effective horizontal stress is about a third of the effective vertical stress. For reverse faulting, maximum horizontal stress is 3 times the effective vertical stress. And for strike slip, sigma h max is going to be about 3 times sigma h min. So actually this term is going to cancel out. So if you have a lot of stress anisotropy, your PV breakdown pressure, it gets smaller and smaller. The less stress anisotropy you have, this PV is going to be bigger. For example, let's assume that we have stresses in horizontal direction, they're all the same. So here you can see that if this one is more or less equal to this one, then your PV contribution to PV of the stress anisotropy is going to be 2 times the effective horizontal stress, which is going to help to get to a higher pressure. So basically this breakdown pressure, it tells you what is the maximum value in which you can get in the pressure in the wellbore without causing tensile fractures. Remember that we said that whenever you increase the pressure in the wellbore, this is going to cause tensile stresses around the wellbore. And if you increase too much the pressure in the wellbore, you can cause tensile fractures. And the equation that now allows us to calculate that is this equation over here. So in order to do an example about this, let's work on a problem. So let me copy this over here. In this problem, you're going to be working on a drilling rig that you want to calculate wellbore stability values at 7,000 feet of depth, and I'm going to ask you to assume that the gradient of vertical stress is 1 psi per foot. I'm going to tell you that this is hydrostatic. It's onshore, so this is that will be the lambda p for offshore. And also, I know that the rock has a tensile strength of 800 psi. In addition to that, I know that in this site, also the minimum principal stress is 4,300 psi, and the maximum principal stress is 6,300 psi. I want you to tell me what is the maximum pressure in a wellbore in this location that you can get to without causing a tensile fracture. So you know everything about this. You know how to solve this problem, because look at the equation. You need sigma h max, you need sigma h min, effective stresses. You know how to do that. You know pore pressure, you know total stresses. You know how to do that. Here I'm giving you those values. In some other problem, I might not give you those values. You have to calculate them on your own. But I'm giving you those values now. And also you have run Brazilian tests that allow you to compute what is the tensile strength of the rock. So tell me what is PV. Tell me what is PV in PSI, but tell me also what is in pounds per gallon, because now we're going into drilling applications. So we need to know those values in pounds per gallon in order to design the drilling mud so that we achieve that pressure in the wellbore. Okay? So I'll give you 3 minutes to finish that. Did you guys use in another course an application which is called hat something, in which you have to use your cell phones to answer things in class? Top Hat? Yeah. Works well? It's okay? Okay. I'm thinking about using it. Okay, so while you solve that problem, let me tell you a little bit about what is called breakdown pressure. It is called breakdown pressure because sometimes, but not always, if you exceed that pressure, you may cause low circulation in the wellbore. You may produce an uncontrolled fracture, tensile fracture that propagates far away from the wellbore, and in which you're going to lose a lot of drilling mud. So because of that, that's why it's called breakdown pressure. Basically, it's like a pipe, right? The wellbore, you may imagine like a pipe. If you increase the pressure too much, it's going to break. So hopefully now you can see that all the applications that we have seen about calculating stresses are very important for solving problems of fault stability, for wellbore stability, and also for hydraulic fracture design, which is what we're going to see in a couple of weeks. Yes, you have the answer?
Yeah.
What did you get?
4320 PSI.
Okay, so can somebody else tell me that in terms of pounds per gallon?
Yeah, 12 pounds per gallon.
Okay. 12, just 12.0?
A little higher than that. I got 4370.
4370. Can you check your numbers again? So let me write. So what is going to be the pore pressure in this place?
3080 PSI.
Okay. What about sigma H max?
3220.
And sigma H mean?
1220.
1220 psi.
Oh, I thought it was you do
Plus. Yes. Sorry about that. Plus the tensile strength, which is 800 psi, right? So you should have got the exact same number, Michael.
Yeah, I used 0.4 for the pore pressure.
Oh, okay. But there was 0.44. But it's okay. You did the right procedure, okay? And this number in pounds per gallon will give you what? Do you have the value in pounds per gallon? 4320.
Is there like a conversion factor for it?
11.8.
Yeah, but basically what you have to do is that value, you multiply it times 8.3, and you divide it, what? But you divide it by the depth and the that should give you a number. Wait a minute, I'm going to write out that. I have something else in my mind right now. So if this is pounds per gallon, then we're saying that, for example, we know that the hydrostatic pressure of water is going to be 8.3, right? So, and you say you calculate about 12, so let's say 8, 9, 10, 11, 12, 13. So 8.3, this is going to be the pore pressure. And that's going to be what? You say, Michael? In pounds per gallon? 12? 11 point something? 11.6. So somewhere around there, we're going to have PV. And
overpressure, like the pore pressure was higher than hydrostatic.
well, no, it's 0.44.
Okay.
Okay? So, so how do we get this number here in ppg? Well, we know that a hydrostatic, the 8.3 pounds per gallon is equal to a gradient of 0.44 psi per foot, right? So if you divide this number by the depth, which is going to be, what is this divided by 7,000? Can you please calculate that? 0.617. Then now multiply this one times that one divided by that one, and that will give you the value in pounds per gallon. Okay. So that 11.64 is this equivalent gradient, but you have to divide it by the depth. Okay. Well, the other thing you could do is a little bit easier. It's the same. This one, you divide it by the depth, that gives you the gradient, right? And then you multiply by this one, divide by that one, and then you get that. It's the same thing. All right. So now we have PV. Okay. That's the maximum value that you could get to by in the wellbore without causing a tensile fracture. Look that it's, in this case, it's higher than PP, considerably higher. So if you were to drill with that pressure, you're not going to cause a tensile fracture. All right? So let's continue. So we have seen tensile fractures. Now let's go to the next case, which is shear fractures. Shear fractures are going to cause what are called breakouts. And basically, in this case, similar to what we had before, if we had the maximum principal stress coming in this direction and the minimum principal stress coming in this direction. Now, the maximum compression around the wellbore is going to be at these locations. You remember? And that's going to be a theta equal to 90 degrees. If you replace the equations of Kirsch for theta equal to pi over 2 or 3 pi over 2, then what you would get is that sigma theta theta. Now, let's recall those equations. Cosine of pi, so now this is going to be pi over 2, right? So pi over 2 times 2 is going to be pi. Cosine of pi is going to be -1. And that -1 now is going to change the sign of those. So when we change the sign of that, let's see how it plays in here. Sigma theta theta, the first part is going to be the same. But now this is going to be positive. And we're going to have 3 sigma h max and 1 negative sigma h mean. And the radial stress is going to be still the same. So now if we want to check whether there is shear failure or not at this location, everything we have to do is just to compare these stresses to a shear failure criterion. And this is the shear failure criterion that we have been using so far, which is just a line, and is that equation. So in this equation, which one is going to be sigma 1 and which one is going to be sigma 3? Around the wellbore, this location. Yes?
Sigma theta theta, sigma 1.
And the other one, sigma 3,
Sigma RR.
is going to be sigma RR. So we just replace these two values in the equation, and what we're going to get is that if this is sigma 1, then we're going to get this minus WPP plus 3 sigma h max minus sigma h mean. That's all of that is going to be equal to UCS plus Q, and sigma 3 is going to be PW minus PP. Notice something very important here that we're going to get to it later on. Sigma 3, it's the confining stress. It's the effective confining stress. By increasing sigma 3, your rock gets stronger. And that sigma 3 in this case, it's the wellbore support. So the more wellbore support you have on the wall of the wellbore, the further you can go in magnitude in sigma theta theta. For example, if in the case of uncemented sands without any cohesion, without any unconfined compression strength, if you don't have any support, you cannot drill a wellbore. So that's why in dry sands you cannot drill a wellbore, because you don't have any support from the sides. If you're not drilling with drilling mat. So the whole objective of the drilling mat is very similar to that membrane that we use for the coffee package, is to provide the support. So something that without the confining stress, it just breaks apart and flows. With the confining stress, it can become a very strong rock. And this is all due to the mud cake and the difference of pressure between the wellbore and the pore pressure in the rock. That applies to support around the wall that allows you to go through a very strong material, even though it's uncemented, because you have an effective stress, still strong. Okay, so this is all just math. What I'm going to do, what I'm not going to do right now, right? But because I want to save some time. But the objective here is just to isolate this pressure of the wellbore on one side, and that one I'm going to call it the pressure of the wellbore that will cause shear failure, or I'm just going to call it PW shear, and the result of that is going to be the equation that I'm writing right now. Which depends on the pore pressure, stress anisotropy, and the strength of the rock. So
That is divided by 1 plus Q.
yes, 1 plus Q. Yeah, this is 1. So again, this is going to be pore pressure. This is going to be the influence of stress anisotropy. And this part is the strength of the rock. Now, conceptually, this pressure means it's going to be opposite to what we had before, that it was the maximum pressure we could get to before we have tensile fractures. Now this is a minimum value. This is the lowest pressure that you can get to in the wellbore without causing failure, shear failure. If you go below that, so if the pressure in the wellbore is lower than this pressure, then you will cause what are called breakouts. Breakouts, which is not other thing but shear failure around the wellbore wall. And I didn't write that in the previous one. So over here, if PW is higher than PV, then this leads to tensile fractures. Okay, so this is going to be a lower bound for the wellbore in the pressure in the wellbore. So let us come back to the problem that we had before and calculate that value. Okay, so I'll leave the equation over there, and now I'm going to add some additional information. I'm going to tell you that the friction coefficient of these rocks is 0.6. It has a UCS of 3,500 psi. So with that additional data and keeping the other variables all the same, you should be able to tell me what is this value PW shear. Okay?